From the videos on slump, VB time and compaction factor test, you have learnt about the properties of concrete when it is still fresh. From the videos on compressive strength, splitting tensile strength, and the static modulus of elasticity and the Poisson ratio, you have learned about the mechanical properties of concrete by breaking it. Fresh and mechanical properties are two major pieces of the puzzle about concrete behaviour. The third piece of the puzzle is equally important. That is the long-term behaviour of concrete. This is known as durability. We use durability indicators to study whether a concrete continues to perform its intended functions. We also use to estimate the serviceability within the expected service life. We can evaluate durability by a simplified and classical service life model. This model separates the service life into two parts. First, carbonation, and second, corrosion. Carbonation is measured by a carbonation test. Two durability indicators of resistance to corrosion are measured by the chloride ion diffusion and the initial surface absorption test. Certainly, there are many other durability indicators, but they have been left for your own study. Carbonation in itself does not deteriorate concrete, but it reduces the pH of the hardened Portland cement paste from between 12 to 13 to a value of about 9 to 10. When we spray phenolphthalein solution over the concrete section, the pink colour represents the area not carbonated. The colourless part represents a carbonated area. Steel in concrete forms a thin passivity film of oxide to protect the steel from corrosion. Maintenance of the passivity film requires a high pH of the pore water. Thus, when the low pH or high chloride concentration front reaches the steel bars, the protective oxide film is removed and corrosion can occur in oxygen and moisture are present. Under steady conditions, the depth of carbon dioxide, D, depends on the square root of time, T, and the carbonation coefficient, K. This coefficient is dependent on the concrete pore system and the cement paste structure. There are 3 steps in performing the carbonation test. The first step is preparation. The second step is cutting and phenolphthalein spraying. The last step is measurement. Watch each step carefully. The first step is preparation. A. Core concrete specimens from the structure, or use moulded specimens. B. Remove large and loose fragments from the cored specimens. The second step is cutting and phenolphthalein spraying. C. Split the cored specimen along the longitudinal axis. D. Clear any dust and loose particles without the use of water or abrasion from the freshly broken surfaces. E. Remove any surface water from the cores and fragments as quickly as possible. F. Indicate the locations and orientations with respect to the original concrete surface. Test the specimen as soon as possible. G. Spray the cut surface with just enough phenolphthalein solution. Complete the test as soon as possible after splitting. The third step is measurement. H. Measure and record at least 3 carbonation depths from the external surface of the concrete to the edge of the red-purpled coloured region. I. Determine the position where the carbonation depth is at its maximum. Measure and record the value. Carbonation depth is dependent on the exposure conditions. Its front propagates much faster into the concrete when optimal temperature and humidity are reached. For example, at 20 degrees Celsius and 65% relative humidity. Now we go back to the surface life model. After the initiation phase, the carbonation depth reaches the still cover depth and starts the propagation phase of corrosion. However, if source of chloride is always present, corrosion in the propagation phase can also start at the same time or before as carbonation does. During corrosion in the propagation phase, chloride ions depassivate the passivity film of oxide over the surface of the still. Corrosion can then take place if oxygen and moisture are present. Corrosion starts with a difference of electrical potential, i.e. anode and cathode, as well as presence of oxygen and water. Thus, the ability of chloride ion passage in concrete is an important measure of how well the concrete can resist chloride. This measure is called the chloride ion penetration test. There are 4 steps to perform the chloride penetration test. The first step is preparation. The second step is specimen mounting. The third step is power connection. And the fourth step is measurement, calculation and evaluation. Watch each step carefully. The first step is preparation. A. Size of the specimen should be 102 mm in diameter and 51 mm in length. B. Cure the specimen well. Details about the curing requirements can be found in ASTM C1202. C. Surface dry the specimen in air for at least 1 hour. D. Prepare epoxy and brush onto the side surface of the specimen. Cure the coating until it is no longer sticky. E. Place the specimen in a vacuum desiccator. Expose both end surfaces of the specimen vertically. F. Seal the desiccator. G. Close the stopcock. Fill the separatory funnel with deaerated water. H. Start the vacuum pump connecting to the desiccator. Observe the pressure to decrease to less than 66.5 millibar within a few minutes. Maintain the vacuum for 3 hours. I. With the vacuum pump still running, open the water stopcock and fill the stopcock continuously with water to make sure that the desiccator is free of air. So, at the same time, the water drains into the desiccator. When the water level covers the specimen, close the water stopcock and allow the vacuum pump to run for 1 additional hour. J. Then close the vacuum pump. Open the stopcock to let the water flow into the re-entry of air into the desiccator. K. Soak the specimen under deaerated water for 18 plus or minus 2 hours. L. Remove the specimen from water. Wipe the excess water. The second step is specimen mounting. M. Place a circular rubber gasket in each half of the test cell. N. Apply a low viscosity sealant around the perimeter of the cell. O. Repeat the above steps on the second half of the cell. P. Insert the specimen and clamp the two halves of the test cell together to seal the specimen. Q. Fill side 1 of the cell with 3% sodium chloride solution. Connect side 1. R. Fill side 2 of the cell 0.3 N sodium hydroxide solution. Connect side 2 to the positive terminal of the power supply. The third step is the power connection. S. Connect the wires with the DC power initial current reading. T. Maintain temperatures of the specimen. Apply the voltage cell and the solutions in a range between 20 to 25 degrees Celsius throughout the test. U. Make sure that the test cell must remain filled with the appropriate solution during the test. The fourth step is measurement, calculation, and evaluation. V. Record the current at least every 30 minutes and for 6 hours. W. Calculate the amount of passed charge that is equal to the summation of the current. X. Evaluate the ability to resist chloride ion penetration by the amount of charge passed according to this table. Proper design of resistant concrete is very important. Crack. Spalling. And delamination are the consequences of chloride ion penetration and subsequent corrosion. When concrete is carbonated, or chloride has depassivated the oxide film of the steel, water and air become the last factors to determine when corrosion of steel happens and how serious it is. Therefore, the absorption of water by the surface concrete becomes crucial at this stage. There are 3 steps in performing the water absorption test. The first step is preparation. The second step is measurement. And the last step is calculation. Watch each step carefully. The first step is preparation. A. Oven dry the specimen. Cool down the specimen in a cooling cabinet. For a non-oven dried specimen, keep it in the laboratory for 48 hours at a temperature of 20 plus or minus 2 degrees Celsius. B. Clean the gasket of the cap. Grease inside and directly on the gasket of the cap with sealant. C. Clamp the cap into position securely. Again, grease around the outside of the cap. Connect the reservoir to the long leg inlet of the cap with a flexible tube. D. Close the tap of the flexible tubing and fill the reservoir with distilled water. Maintain a water head from 180 to 220 millimeters. The second step is measurement. E. Open the tap to allow the water to run into the cap and start the stopwatch. When the water arrives at the top of the cap, connect the capillary and scale to the short leg outlet with the second flexible tube. This action drives air more effectively out from the cap. F. Examine the sealing of the cap. If any sign of seepage is observed, either stop the test or repair the perimeter of the cap with sealant. G. Flush all the air within the cap through the capillary tube by pinching the flexible tubing and suction from the end of the capillary tube. H. Refill the reservoir to maintain a water head of 180 to 220 mm. Ensure that the reservoir always contains water. I. Take readings after 10 minutes, 30 minutes, and 1 hour from the start of the test. J. At each test interval, close the tap to allow water to flow back along the capillary tube. Start the stopwatch at the same time. K. Count 5 seconds and note the divisions as the menicus moves. When the count is less than 3 divisions, record the scale division after 2 minutes. L. When the 5-second count is more than 3 and less than 9 divisions, record the scale division after 1 minute. M. When the 5-second count is more than 9 divisions, record the scale division after 30 seconds. N. When the measurement has been completed, open the tap. The third step is calculation. O. When 30-second or 2-minute readings are taken, multiply the number of scale divisions by 2 or 0.5 respectively to convert the reading to a 1-minute period. P. The initial surface absorption is equal to the number of scale units traversed per minute times 0.01. The dimension is milliliters per square meter seconds. Q. Going back to the 5-second count, if the movement in the 5 seconds moves more than 30 scale divisions, the concrete is very permeable, and so record the initial surface absorption as more than 3.60 milliliter per square meter. R. If the 10-minute reading after the start of the test is below 5 scale divisions, stop the test and comment on the result as concrete too impermeable to be sensitive to a longer-term test. Similarly, when the same reading exceeds the scale, stop the test and record the result with the comment concrete too permeable to be within the sensitivity of the test method. Higher initial surface absorption means the concrete is more permeable and more vulnerable to attack from external agents. Water, carbon dioxide, oxygen, and aggressive ions are the principal fluids and gases intruding into concrete. Concrete durability depends on the ease with which these fluids and gases can penetrate concrete by diffusion and sorption. The measure of the ability of fluid and gas to penetrate is known as permeability. The lower the permeability the concrete achieves, the better and more durable it is. Lower concrete permeability can be achieved by the mixed design, such as a lower water to cement ratio, and the inclusion of blended cement to produce high-performance concrete. Examples of blended cement are fly ash, silica foam, and slag. Pozzolans in the blended cement can effectively disperse over and blend it into cement. its pozzolanic reaction and microfiller effect block the continuity of the pores, and so lower the permeability. These durability tests are used all over the world. These procedures are standardized in British, American, and Hong Kong construction standards. A few of the most important durability issues are highlighted in this video. There are many other mechanisms to affect concrete durability, such as sulfate attack, alkali silica reaction, freeze-fall damage, etc. These mechanisms are left for your further study. By watching this short video, we hope you have been able to understand 3 main points: the procedures and the underlying principles of the durability tests for concrete, the reasons for carrying out the durability tests, and concrete permeability as the primary factor affecting concrete durability. Next time, if you see concrete cracking, spalling, or delamination in a concrete structure, will you be able to tell what is happening, why, and how?